Hello my friends and welcome back to the You Can Do TV channel. In heavy-duty power transmission, precision assembly defines performance. At Horsburgh & Scott, heat expansion assembly of industrial gears ensures an interference fit engineered for maximum torque transfer and concentric stability. Controlled thermal expansion allows gears to be mounted onto shafts without inducing mechanical damage. In-house heat treatment capabilities, including gas carburizing, induction hardening, stress relieving and through hardening, optimize surface hardness, core toughness, and dimensional integrity to meet demanding load and wear requirements. State-of-the-art gear manufacturing at Horsburgh & Scott integrates heavy-duty handling with ultra-precision machining. With a 75-ton crane capacity, massive gear blanks are safely positioned for processing in advanced gearing centers. Operations include gear cutting, hobbing, gashing and specialized profile generation, all executed under strict process control. High-rigidity machine platforms and optimized tooling ensure dimensional stability during roughing and finishing. Final verification is performed using precision metrology systems capable of measuring gear geometry within 2 microns, confirming tooth profile accuracy, lead alignment, and pitch consistency for industrial power transmission applications. Industrial gear rebuild and repair demand precise engineering control at every stage. Damaged gears are disassembled, dimensionally inspected, and analyzed for wear patterns, pitting, or tooth profile deviation. Reverse engineering techniques restore original geometry when drawings are unavailable. Heat treatment, stress relief, and precision machining re-establish hardness and concentricity. Final assembly includes controlled backlash setting, contact pattern verification, and dynamic testing to ensure restored load capacity and operational reliability. Drive engineering in steelmaking plants and rolling mills must withstand extreme torque loads, thermal stress, shock forces, and continuous operation over decades. SMS Group develops and manufactures heavy-duty drive systems, engineered for maximum reliability, product quality, and long-term plant availability. Gear manufacturing at SMS Group is built on vertical integration and process control at every stage. At the Hilchenbach workshop, large gears are produced with modules up to 40 and diameters reaching 6 meters, supported by a modern, high-capacity machinery pool. Production of a large gear wheel begins in the welding shop. Fully mechanized submerged arc welding is applied to all joints to ensure deep penetration and consistent weld quality. After welding, the gear blank undergoes stress relief heat treatment to eliminate residual stresses and stabilize the structure before machining. Advanced milling and turning centers then machine the blank under strict dimensional supervision. For high-load applications, such as hot rolling mills, double helical gears weighing up to 45 metric tons and measuring 4.5 meters in diameter are case-hardened to achieve a wear-resistant surface with a tough core. Ultrasonic testing follows heat treatment to verify material integrity, particularly in critical tooth root zones. Tooth flanks are then precision ground on profile grinding machines to achieve exact involute geometry and optimized load distribution. Each finished gear is inspected on dedicated high-precision measuring machines to confirm profile accuracy, pitch deviation, and runout within micron-level tolerances. Gear housings are manufactured in-house and machined for precise alignment. Complete gear units are pre-assembled, and contact patterns are adjusted using eccentric sleeves, allowing fine-tuning of backlash and load sharing, even compensating for foundation settlement after years of service. From welding and machining to assembly and inspection, SMS Group delivers fully engineered drive systems designed for extreme torque, durability, and long-term operational stability in demanding steelmaking environments. Generator, stator, and rotor repairs demand a combination of precision metrology, electrical expertise, and heavy mechanical capability. At the Farmington, New Mexico facility, advanced ferro arm measurement systems capture high-resolution dimensional data to assess wear, deformation, and alignment across large rotating components. This data supports detailed component engineering and repair planning. Rotor winding operations involve complete removal and replacement of field windings, insulation systems, and retaining rings where required. Following rewinding, rotors undergo high-speed dynamic balancing at speeds up to 150 RPM, ensuring vibration levels meet stringent operational limits for reliable turbine generator performance. On the stator side, comprehensive electrical testing evaluates insulation integrity, partial discharge levels, and core condition. Replacement stator bars, manufactured by Ethos Energy in Lubliniec, Poland, are produced to exact specifications before shipment for installation. Stator rewind projects include bar removal, slot preparation, precision bar installation, connection brazing, and full assembly. Supporting these processes, in-house machining of parts restores critical tolerances on shafts, journals, coupling fits, and structural components, returning generators to dependable, long-term service. What does it take to return a decade-old hydrogenerator to peak performance in the demanding climate of the Yukon? A 10-year overhaul of a Whitehorse hydrogenerator is a comprehensive engineering operation that restores reliability, efficiency, and structural integrity. The process begins with a controlled shutdown, followed by complete disassembly of the turbine generator unit. The rotor is lifted using heavy-capacity overhead cranes, while the stator, bearings, and excitation systems undergo detailed inspection. Dimensional checks, non-destructive testing, and insulation resistance measurements identify wear, thermal degradation, and mechanical fatigue. Critical components such as guide bearings, thrust bearings, seals, and cooling systems are refurbished or replaced. The rotor is cleaned, rebalanced, and tested to ensure vibration levels remain within strict tolerances. After reassembly, alignment verification, electrical testing, and commissioning confirm the generator is ready to deliver another decade of dependable, renewable power. Installation of the Wusquateam runner, marks the transition from heavy civil construction to high-precision mechanical and electrical assembly. With major concrete and structural work complete, focus has shifted to turbine and generator integration, where tight tolerances govern every step. One of the largest lifts inside the powerhouse involved relocating a rotor into temporary storage to optimize sequencing and maintain schedule. Such hydro projects demand meticulous alignment of massive components, each requiring exact positioning to ensure vibration control and long-term reliability. Engineering teams addressed early logistical and installation challenges through coordinated planning and adaptive execution. As assembly advances toward final alignment and first rotation, the project enters its most technically demanding and rewarding phase. In a world where sustainable energy is no longer optional, Global Hydro focuses on high-efficiency Francis runners engineered for medium head applications in stable flow conditions. Development begins with advanced hydraulic design, combining CFD simulations, flow testing, and collaboration with international research institutions to guarantee performance and efficiency targets. Once the 3D design is finalized, CAM programming and machining simulations define milling duration, material removal rates, and collision control. The runner is typically machined from 1 or 2 forged monoblocks of high-alloy stainless steel, selected for strength and erosion resistance. Using a 7-axis CNC machining center, complex blade geometries are milled in a single setup, with machining times reaching up to 400 hours depending on size and material. After machining, surfaces are hand-polished, and split runners undergo heat treatment. Each runner is dynamically balanced to ISO standards. Digital 3D measurement verifies contour accuracy before assembly. Final pressure testing of the spiral casing ensures weld integrity and structural safety. The result is a precision-engineered Francis turbine designed for long-term, high-efficiency hydropower generation. The Ramshorn Cranehook 25V, manufactured in accordance with DIN 15402, is forged from high-strength alloy steel 34CR292 Mo to ensure superior load-bearing capacity and fatigue resistance. After forging and heat treatment, the hook undergoes precision CNC milling to achieve critical dimensional accuracy. Machining operations focus on contour profiling, shank geometry, and load-bearing surfaces, using multi-axis milling centers to maintain tight tolerances and smooth surface finish. CNC control guarantees repeatability, optimized stress distribution, and precise compliance with DIN 25V specifications for heavy lifting applications. The Zenith 400 by PTG Holroyd represents a new generation of precision helical profile grinding technology, engineered for high accuracy, productivity, and process control. With capacity for components up to 420 mm in diameter and 700 kg in weight, the machine combines compact footprint with exceptional versatility. It supports a full range of abrasives, including vitrified aluminum oxide, vitrified and plated, enabling both fine finishing and aggressive semi-finishing with high stock removal rates. A fully automated wheel balancing system ensures stable operation at speed, while advanced in-process dressing maintains profile integrity. The integrated Holroyd 3D scanning probe provides automatic measurement and closed-loop compensation via software, guaranteeing Micron-level accuracy. Twin operating modes, intuitive touchscreen programming, automatic parameter verification, and rapid setup streamline both production and development environments. PTG Holroyd's Precision Rotors Chongqing manufacturing facility represents a vertically integrated approach to high-accuracy rotor production for compressors, vacuum pumps, and related rotating equipment. The plant is engineered around controlled process flow, digital manufacturing systems, and precision metrology, ensuring repeatable geometry at micron-level tolerances. Production begins with carefully specified alloy steel billets, selected for mechanical strength, dimensional stability, and machinability. After incoming material verification and ultrasonic inspection, blanks undergo rough machining on high-rigidity turning centers. This stage establishes datum features and removes excess stock while maintaining strict concentricity control, critical for downstream helical profile generation. The core of the facility is dedicated to precision helical milling and grinding. Advanced multi-axis machining centers generate complex rotor profiles using proprietary toolpaths developed through integrated computer-aided design and computer-aided manufacturing platforms. Thermal stability within the machining environment is tightly regulated to minimize dimensional drift. Semi-finishing operations balance material removal rates with surface integrity, preparing components for final grinding. High-precision rotor grinding is performed on specialized Holroyd machines, capable of maintaining exact profile accuracy along the entire rotor length. In-process measurement systems continuously monitor geometry, enabling automatic compensation for tool wear and thermal variation. Surface finish is optimized to support efficient gas sealing and long-term operational durability. Following profile generation, rotors undergo dynamic balancing to reduce vibration at operational speeds. Correction procedures are executed with minimal material removal to preserve geometric fidelity. Where required, heat treatment and stress relief cycles are applied under controlled conditions to stabilize the metallurgical structure before final finishing. Metrology is fully integrated into production. Coordinate measuring machines, scanning probes, and profile analysis systems verify lead, pitch, involute form, and runout. Data is recorded within a digital quality management framework to ensure full traceability, from raw material to finished rotor. Assembly support operations, including shaft fitting and keyway machining, are performed with strict alignment control to guarantee optimal integration into compressor housings. Each rotor is subjected to final inspection before protective packaging for global shipment. The Chongqing facility reflects a manufacturing philosophy centered on precision engineering, process control, and continuous improvement. By combining proprietary grinding technology with advanced measurement and disciplined workflow management, the plant delivers high-performance rotors designed for efficiency, reliability, and long service life in hard industrial applications. France's turbine machining demands extreme dimensional accuracy and controlled material removal. Large stainless steel or martensitic cast components are clamped on heavy-duty multi-axis machining centers. CNC milling and turning operations shape blade profiles, hub interfaces, and sealing surfaces to tight tolerances. Continuous measurement, vibration control, and surface finishing ensure hydraulic efficiency, balance, and long-term structural reliability under high-pressure flow conditions. As demand for sustainable energy intensifies, precision manufacturing becomes central to small hydropower performance. The production of a Pelton runner begins with advanced three-dimensional design using computer-aided systems optimized through hydraulic simulation to maximize efficiency. A monoblock disc of high-grade stainless chromium nickel steel undergoes strict material inspection before machining. The runner is then milled on a 5-axis computer numerical control machining center, where complex bucket geometry is rough machined, then finish milled with simultaneous multi-axis movements. Programming and simulation ensure accurate tool paths and collision control. Grinding, polishing, and static, as well as dynamic balancing, complete the process. The result is a high-efficiency Pelton runner engineered for durability, repeatability, and long-term operational stability in small hydropower plants. This prime turning demonstration showcases the complete machining of a pinion in just 40 seconds. The operation progresses seamlessly from aggressive roughing to precision finishing using Rotor Prime B-type and A-type tools. By enabling cutting in all directions, the method supports higher cutting speeds, increased feed rates, and extended tool life, delivering a substantial boost in productivity and process efficiency. At Machine and Fabric Alfing Kessler, the BAZ-2 Machining Center represents precision heavy-duty manufacturing at its highest level. Designed for complex crankshaft and large component processing, BAZ-2 integrates rigid structural design with high torque spindle performance. Multi-axis machining enables accurate milling, drilling, and contouring in a single setup. Advanced control systems ensure repeatable tolerances, optimize cycle times, and stable cutting conditions, even under demanding material removal rates. Inside a 20,000 m² production facility, the manufacturing of bandsaw and circular saw blades is driven by precision, metallurgy, and process control. Production begins with carefully selected raw material, including stainless steel grade 321, chosen for its high temperature strength and corrosion resistance. Steel is processed into blade blanks through close tolerance cutting operations that ensure dimensional stability from the outset. High-performance sawing systems, such as KR saws and King-Kelder equipment, demonstrate the efficiency of modern blade technology. A 117 mm diameter stainless steel bar can be cut in just 23 seconds per cycle, achieving up to 750 total cuts while maintaining a polished surface finish. This combination of speed and surface integrity reflects optimized tooth geometry, advanced carbide tipping, and vibration-controlled machine setups. Following blank preparation, blades undergo heat treatment to refine microstructure, CNC grinding to achieve precise tooth profiles, and surface finishing to reduce friction and heat buildup during operation. Each stage is monitored to maintain strict tolerances and repeatability. The result is a cutting tool engineered for durability, consistent performance, and high material removal efficiency, where metallurgy, machining accuracy, and production scale converge to define modern saw blade manufacturing. A 3,000-ton hot forming press transforms heavy steel plate into precision tank heads, dish heads, and pressure vessel components built for extreme service conditions. The process begins with controlled heating of the plate to forging temperature, enhancing ductility and reducing forming resistance. Under massive hydraulic force, the press drives the heated material into a die, shaping hemispherical or toruspherical profiles with uniform thickness distribution. Real-time pressure and stroke control ensure dimensional accuracy and repeatability. The result is a structurally refined vessel head with optimized grain flow, improved strength, and reduced residual stress for industrial applications. Roll threading is a cold-forming extrusion process widely used in fastener manufacturing to produce high-strength, precise threads without material removal. Instead of cutting, reduced diameter round bar is forced between hardened dies that plastically displace the steel, forming the thread profile. The starting bar diameter corresponds approximately to the pitch diameter. For example, a 1-inch bolt is rolled from about 0.912-inch stock. After rolling, the threaded section achieves full major diameter, while the shank remains reduced. This method improves surface finish through burnishing, enhances fatigue strength via work hardening, and optimizes grain flow along the thread contour. Roll threading increases production efficiency, reduces material waste, and lowers weight-based costs such as heat treatment, coating, and freight. Great Wall Steel Casting Company operates a professional and fully integrated steel casting foundry process designed to deliver high-performance industrial components. The production cycle begins with strict raw material selection and chemical composition control to ensure consistent steel quality. Scrap steel and alloy materials are melted in electric arc furnaces, followed by refining and precise temperature adjustment. Molten steel is then poured into custom-designed molds for products such as slag pots and slag ladles. For customized slag pots and slag ladles, advanced casting simulation software is used to optimize structure, wall thickness, and thermal resistance. After solidification, castings undergo heat treatment to enhance strength, wear resistance, and impact toughness. Machining, dimensional inspection, ultrasonic testing, and magnetic particle testing ensure each product meets international standards. Surface treatment and final quality checks are performed before delivery. With strict quality control and rich manufacturing experience, Great Wall Steel Casting provides durable, customized solutions for steel mills and heavy industry worldwide. Manufacturing DIN 7992 Hammerhead T-bolts combines controlled forming and precision machining to achieve high structural reliability. Production starts with upset forging, where heated steel bar is plastically deformed to form the hammerhead geometry, while refining grain flow for enhanced strength. Subsequent machining ensures accurate head dimensions and shank tolerances. Threads are then produced by roll threading, a cold-forming process that displaces material to create dense, work-hardened threads with superior fatigue resistance. Final inspection verifies dimensional compliance before automated packing prepares the bolts for secure transport and industrial application. Steel production at Nucor follows a fully integrated high-efficiency route built around the electric arc furnace. The cycle starts in the scrapyard, where recycled steel is sorted and prepared before being charged into the furnace. Powerful electrical arcs generate extreme temperatures, rapidly melting the scrap. During refining, slag forms to absorb impurities and is removed before the clean molten steel is tapped into a ladle. Secondary metallurgy takes place at the ladle metallurgy furnace, where chemistry and temperature are precisely adjusted to meet specification. For demanding grades, the steel is further treated in a vacuum tank degasser to remove dissolved hydrogen and nitrogen, improving internal soundness. The ladle is then transferred to the continuous caster. A rotating turret exchanges empty and full ladles, feeding steel through a tundish into the mold to form solid blooms. Once cut and cooled, blooms are charged into the rolling mill reheat furnace. After reheating, high-pressure descaling removes surface scale before the reversing breakdown mill reduces the section. Cropping trims the front end, and inline rolling progressively shapes the bar. Final operations include controlled cooling, shot blasting, chamfering, dimensional verification, and inline non-destructive testing to ensure mechanical integrity and surface quality. A pipe twisting machine designed for 114 mm diameter tubes delivers controlled torsional forming for medium-sized steel sections. The pipe is secured in heavy-duty hydraulic clamps, while a servo-driven spindle applies calibrated rotational force. Torque, twist angle, and rotational speed are precisely regulated to prevent wall thinning, buckling, or cross-sectional distortion. For structural-grade pipes, internal mandrel support or reinforced gripping jaws ensure dimensional stability throughout the twist cycle. CNC programming enables consistent pitch and repeatability, making the system suitable for architectural columns, structural components, and industrial frameworks requiring accurate, uniform helical deformation. The Yumuko forging and pressing line represents a fully integrated production system for manufacturing high-strength steel housings through controlled thermal processing, precision forging, automated handling, and subsequent machining operations. Production begins with an automatic storage and feeding magazine that supplies steel bars to an induction heating installation manufactured by Brown Boveri. This unit operates at 450 kilowatts with a heating frequency of 500 Hz, ensuring uniform through heating of bars up to 130 millimeters in diameter. Once the target forging temperature is achieved, the heated bars are transferred to a hydraulic shearing press manufactured by FICEP, where they are cut into precise billets for downstream forming. The primary deformation stage is performed on a hydraulic forging machine manufactured by Yumuko, designed for steel housings weighing up to 50 kilograms. The system consists of two functional sections. The first section performs upsetting and piercing, with a forming force of 630 tons and a ram stroke of 250 millimeters. The second section carries out elongation and calibration using rollers and rings, delivering 200 tons of force with a 200 mm stroke to achieve accurate geometry and grain flow optimization. A robotic stacking unit automatically arranges the hot forgings into pallets for normalization heat treatment, ensuring consistent metallurgical properties. The machining line incorporates a programmable hydraulic copying lathe for high-efficiency rough turning, followed by a programmable finishing lathe that achieves final dimensional tolerances and surface requirements. An automatic technological module dedicated to shrink-fitting operations includes an automated loading magazine, a 375 kilowatt induction heating system operating at 1000 Hz manufactured by Electro Machine and Schulze, a vibratory forging machine manufactured by Useem de Wecker for controlled radial contraction, and 2 synchronized manipulators that ensure precise positioning and safe handling throughout the process. A small diameter pipe twisting machine is engineered to impart controlled torsional deformation to thin-walled tubes without compromising structural integrity. The process begins with precise clamping to prevent axial slip, followed by synchronized rotational force applied through servo-driven spindles. Torque, angle, and speed are digitally monitored to ensure uniform twist pitch and avoid wrinkling or ovalization. For smaller pipes, accurate mandrel support is critical to maintain internal diameter stability. CNC control enables repeatable twist patterns, making the machine suitable for decorative metalwork, heat exchanger components, and lightweight structural applications requiring consistent geometric precision. White-hot steel glows beneath the hammer, its structure transforming with every controlled strike. Closed die forging technology harnesses this intense force to reshape heated metal inside precision machine dies, producing components of exceptional strength, toughness, and dimensional accuracy. Each impact refines the grain structure, eliminates internal voids, and aligns the metal flow along the geometry of the part. The result is a dense, homogeneous microstructure engineered to withstand extreme mechanical stress. Unlike casting, where molten metal solidifies in a mold, closed die forging plastically deforms solid billets under compressive loads. Carefully controlled temperatures, die design, and press or hammer energy determine material flow and final properties. Advanced forging presses, ranging from mechanical and hydraulic systems to ultra-large drop hammers, deliver immense force, enabling the production of heavy-duty components such as crankshafts, connecting rods, gears, hubs, and structural parts for construction and rail equipment. Modern facilities integrate simulation software to predict material behavior, optimize die filling, and minimize defects. Post-forging operations such as trimming, heat treatment, machining, and non-destructive testing further enhance performance and reliability. Precision-controlled processes ensure repeatability even in complex geometries. Closed die forging stands at the intersection of raw power and metallurgical science. By combining controlled deformation, thermal management, and expert die engineering, this technology produces lighter, stronger components capable of operating in the harshest industrial environments. It remains a cornerstone manufacturing method for industries demanding uncompromising structural integrity and long service life. A wind turbine tower may appear as a simple steel column on the horizon, yet its production demands advanced heavy fabrication and strict quality control. Manufacturing begins with thick structural steel plates, typically 20 to 40 millimeters thick, prepared through shot blasting to remove scale and enhance weld adhesion. CNC plasma or oxy-fuel cutting systems shape each plate to exact dimensions. The plates are rolled into cylindrical shell sections using high-capacity plate rolling machines. Longitudinal seams are welded by automated submerged arc welding, delivering deep penetration and consistent mechanical strength. Forged flange rings are welded to both ends of each section, enabling bolted assembly on site. All welds undergo non-destructive testing, including ultrasonic and radiographic inspections, to verify structural integrity. Internal components such as platforms, ladders, and cable routing systems are installed before surface finishing. Surface treatment is critical. The sections are grit blasted to a controlled roughness, then coated with a multi-layer protective paint system, zinc-rich primer for corrosion resistance, intermediate epoxy layers for barrier protection, and a durable polyurethane topcoat for UV and weather resistance. Completed tower segments, often weighing dozens of tons, are then transported for final erection at the wind farm site. Behind every precision brass fitting lies a tightly controlled manufacturing chain. At Cavaletto, the process begins with engineering design, where dimensions and tolerances are defined. Raw bar or tube stock is cut to length, then heated to optimal forging temperature. High-pressure presses shape the heated brass into near-net forms. After cooling, components move to CNC machining centers for threading, boring, and dimensional finishing. Automated transfer systems handle internal transport between stations, reducing handling errors and improving efficiency. Each stage is monitored to ensure structural integrity, surface quality, and strict compliance with industrial standards. – 2017 marked the fourth year of the monumental Obervermundwerk 2 project in the Silvretta Mountains. For the teams on site, this meant the construction works were finally entering the home stretch. Throughout this year, massive progress was made across various sections, proving that human ingenuity can indeed master the raw power of the Alps. Deep within the mountain, 800 meters below the surface, lies the machine cavern, a colossal man-made void. Here, the structural concrete work is largely complete. The massive spirals for the turbines and pumps are already partially embedded in concrete. Currently, the teams are focused on the steel hydraulic engineering components, such as installing the gate boxes in the tailwater area. By the end of 2016, both the machine cavern and the adjacent transformer cavern were structurally finalized, setting the stage for the mechanical heart of the plant to be installed. In the 2.8-kilometer-long Silvretta tunnel, work continued day and night on the concrete lining. Following the successful excavation in 2016, the inner shell was cast. This was a rhythmic industrial ballet. A giant shuttering carriage moved forward in 14-meter sections, acting as the mold for the concrete. Each section required approximately 220 cubic meters of concrete, totaling a staggering 45,000 cubic meters for the entire tunnel. One of the most complex tasks was the junction where the connecting tunnel leads to the surge tank, requiring intricate reinforcement work to withstand future hydraulic forces. At the lower end of the Silvretta pressure shaft, workers spent 5 months assembling the Hosenrohr, or distribution pipe. This Y-shaped massive steel structure splits the water flow from the main shaft into the 2 separate machine units. Piece by piece, these steel sections were transported into the mountain and welded together with absolute precision. Once finished, this vital component was encased in meters of concrete, hidden forever from view, accessible only to inspectors during future maintenance. While concrete dried on site, the organs of the power plant were being birthed across Europe. In Ravensburg, Germany, the guide vanes for the turbines took shape. In St. Polten, Austria, the pump impeller was machined from a single casting, refined to the 100th of a millimeter. This is where heavy machinery meets fine craftsmanship. In Switzerland, at General Electric, the generator components were under construction. The stator, the stationary part of the generator, required 108,000 individual steel plates to be stacked by hand. This 150-ton component will eventually be flooded by a rotating magnetic field to produce the electricity that powers thousands of homes. In Völklingen, Germany, the Saarschmiede, one of the largest open-die forges, crafted the 4 rotor shafts. Starting as a single block of steel heated to glowing temperatures, a press with 12,000 tons of force shaped the 36-ton workpieces. These shafts were then sent to Italy, near Venice, where they were machined on lathes to their final, precise geometry. Back in Linz, Siemens workers hand-built the 200 MVA transformers. Weighing 152 tons each when empty, these are the heaviest single components to be transported to the site. The logistics are a feat of their own. Using a 64-wheel self-propelled modular transporter, these giants were moved up the winding Silvretta High Alpine Road at night. The transporter can adjust its height and tilt to compensate for the steep gradients and sharp hairpin turns, ensuring the 200-ton total load remains stable. Inside the cavern, the assembly of the first machine set is moving at high speed. The upper half of the stator, weighing 112 tons, is lowered onto the lower half. The rotor, with its 14 magnetic poles, each weighing 7 tons, is inserted with a tolerance of just 1 millimeter. This requires fingertip feel from the crane operators, as the total weight exceeds the capacity of a single crane, necessitating a tandem lift using both haul cranes. Outside, despite the winter weather, work continued on the intake structures. Before the spring snowmelt, the Silvretta reservoir was lowered to allow for the breakthrough between the intake building and the Silvretta tunnel. Once the final 40 meters were blasted, massive trash racks were installed to prevent debris from entering the system. Back in the tunnel, 2.5 million liters of a cement-water mixture were injected behind the concrete shell to solidify the surrounding rock, ensuring the system can handle the immense internal pressure. By late 2017, the tailwater area was flooded for the first time, tested meticulously for leaks. As the year draws to a close, the electrical engineers are busy installing the 220 kV gas-insulated switchgear and connecting the 4.9 km-long high-voltage cables that run down the valley. After 1.5 million man-hours, the ambitious goal is within reach. The wheels are beginning to turn, the steel is set, and the mountain is ready. Thanks to the tireless work of engineers and laborers, Oberwehrmann Work 2 is on track to go into operation by the end of 2018, standing as a testament to the power of modern engineering. Explosion Bond Clad Pressure Vessel Fabrication at Contract Fabricators Inc. combines advanced metallurgical bonding with heavy-duty vessel manufacturing. Dissimilar metals are joined through controlled explosive bonding, creating a high-integrity clad plate with exceptional corrosion resistance and structural strength. Plates are then formed, rolled, and precision welded into pressure vessel shells under strict code compliance. Dimensional control, non-destructive examination, and heat treatment ensure mechanical performance and bond integrity. The result is a pressure vessel engineered for extreme temperatures, high pressures, and aggressive process environments. From a simple steel strip to a precisely engineered cutting blade, every movement inside this forming line is calculated. The coil is straightened, radius bent, and twisted to match the mower cylinder profile. An integrated CNC measuring system verifies geometry before trimming, ensuring dimensional accuracy and consistent production quality. The production of chrome steel balls and S2 rockbit balls follows a tightly controlled metallurgical and machining sequence to ensure high hardness, wear resistance, and dimensional precision. Alloy steel wire or bar is first cold formed into spherical blanks, then subjected to soft grinding to remove flash and establish basic roundness. Heat treatment is performed in a fully automated line integrating controlled heating, quenching, cleaning, and tempering stages. Precise temperature control and quench parameters create a uniform martensitic structure with optimized core toughness and surface hardness. Automated electronic monitoring ensures repeatability and process stability. Following heat treatment, the balls undergo hard grinding and multi-stage lapping to achieve micron-level sphericity and low surface roughness. Advanced inspection systems, including photoelectric sorting and eddy current testing, detect surface and subsurface defects. Final cleaning, dimensional verification, and automated packaging complete the process, delivering high-precision balls for bearings, wind turbines, and drilling equipment.